So if you want to learn about graph theory, you probably want to learn who is Leonard Euler. Leonard Euler was a very cool guy, and he invented graph theory. He did a lot of things, by the way. In fact, he's famous for many mathematical theorems, and an example would be something like e to the I pi is equal to -1. So this guy is fantastic, and he also invented graph theory. And when he invented graph theory, it was in order to solve this problem, called the 7 bridges of Konigsberg. So what was the 7 bridges of Konigsberg problem? Well, we can talk about it quite easily by just asking the question. This was the problem of the day. Can you find a walk through this city where there's this river that goes through the city so that you cross every single one of these bridges once and only once? So there are 7 bridges, so it makes sense to call it the 7 bridges of Konigsberg. Now, you don't have to start and end in the same place, so you might want to start over here and end over here or something like that. And you have to cross every single bridge exactly once. And you're not going to be doing things like going halfway over and then coming back. You've got to go all the way across, and then once you're over here, you've got to go across another bridge. So the point was, can you get around the city, crossing all of these bridges once and only once? So this was a very famous problem. Why don't we give it a go? What we're going to do is just give it a try. Let's say we start at this part of the city. And maybe we walk across this bridge, and now we're in this little islandy part. And maybe we decide to go this way, and we're over here now. And what are we going to do? Maybe let's just go somewhere we haven't been yet. We'll go across that bridge. So by the way, every time I've used this bridge, and this bridge, I can't use them again. So now I really have no choice but to go across one of these 2 bridges and end up back to this part of the little islandy part. And now that I'm stuck here, I really could go either across this bridge or across this bridge. And let's say I was to do this. Well, I'm going to be very stuck now because there's nowhere for me to go from here. I've already used the bridges that are this bridge here, and this bridge here, so I'm going to be very stuck. So maybe I don't do that, and maybe I decide to go this way. Well, now that I'm here, I only have 1 bridge left to go over, and now I go here, and I'm stuck again, and I didn't use this bridge. Oh man, this seems difficult, right? Well, it turns out that this question, can you find a walk through the city that crosses each bridge exactly once? The answer is no, you cannot. The reason is not because I cannot just do it via some example. The reason is more complicated than that. And Euler is the one who solved this problem, and he solved it using graph theory. But there was no such thing as graph theory at the time. So how did he think about it? What he did was he said, okay, well, this seems like a geometry question or a topology question, but really it's not. All you care about in this question is that there's this piece of landmass and this piece of landmass and this piece and this piece. And then you also care about the relationships between those. So I'm going to draw in red. This is a relationship between these landmasses, and this is another relationship, and this is another relationship. These bridges are just relationships between the parts. And it does not matter how the city is laid out over here or over here. It doesn't matter what the water looks like or the bridge or anything like that. None of this matters. Angles don't matter. Topology doesn't matter. It's just about the relationships between these blobs and these lines. And that is the fundamental idea of graph theory. In fact, graph theory is an entire subject of mathematics on its own, and this was the very first example solved using graph theory. So let's try to draw this in a better way. Instead of thinking about the complicated city, we're going to think about this as a landmass, this as a landmass, one, and this one. So you can see that I've drawn them as 3 things. These are representing these 3 blobs in a row, and then one off to the side represents that landmass off to the side. Now again, I'm going to use red to connect them up. And I notice that the landmass at the top has 3 things that come off of it, 3 bridges. 1 goes to this guy. 2, in fact, go to this islandy thing. And if you look down at the bottom, you again have 2 bridges that go to the island, and again, 1 that goes across here. And don't forget that you have a bridge right here in the middle that goes from here to here. So this picture describes exactly everything you need to know in order to figure out the problem. So what is this right here? Well, let me draw these vertices a little bit darker. And when I say vertices, that's because that's the technical definition in terms of graph theory. These green bits right here are actually called vertices. Sometimes you'll hear them being called nodes. It's the same thing. And what about these red bits, these lines that go between the green bits? These things are called edges. Okay, so we have this idea of a graph which has some dots and lines, which are vertices and edges. And the question now is, can we move through this graph so that we hit every single one of these edges exactly once? So if I was to use this edge, I can never use it again, and I have to go through here, use this edge, and never use it again. So in order to understand why this one is impossible, it's a good idea to try an example of something that does work so that we can see what it is that's going wrong when it doesn't work. So let me draw an example where we will have a solution. Maybe I'm giving you a bit too much of a hint to tell you that there will be a solution, but we can work this out together. So this is my new graph. As you can see, it looks very similar, except I'm missing one of these bridges that goes right through here in this edge. And so what I'm going to do now is I'm going to try to find a walk that uses every single one of these red edges exactly once. And let's see if I can do that. What I'm going to do is I'm going to start at this bottom vertex here, and I'm going to use one of these edges up. Then I'm going to go up again, and then come back again, and back again. Now I can never use any of those four edges again. And I go to this one, and then to this one. So I've just used every edge exactly once. Notice that I started here, start at this vertex, and I ended here at this vertex. So what I just found here is an example of what is now called an Eulerian walk. It's not a coincidence, it's because this guy Euler is the guy who started it all. So this is called an Eulerian walk. And what we want to do is think about why the Eulerian walk worked here and why it won't work over here. So I'm just going to scroll down so we have a little bit more space. And let's think about any vertex that we might have. And what we're going to do is just think about what would happen if it had an odd number of lines or edges touching it, and what would happen if it had an even number. So let's draw two things like this, and then I'm going to give them some edges. Over here, I'm going to do an even example, and over here, I'm going to do an odd example. So let's say I have some even number of things, and over here, I have some odd number of things. Okay, so let's see if we can understand what is the fundamental problem. If I have an even degree vertex, now I'm using this word degree. What does the degree mean? It just means the number of edges that are a particular vertex. So here the degree is 4 in this particular picture. So if I take a look at something that has degree 4, and I say, okay, I'm going to enter in on some sort of edge, and I come in like this, do I have a way of exiting? Yes, I do. Right now, I still have a way to exit. And then maybe I continue on in my walk somehow, and eventually I'm going to come and visit this vertex again because this edge right here has not been used. So I'm going to enter right here, and then I ask, can I get out again? Can I leave? And sure I can leave this way. So this is very, very good for all the vertices that are not start and end vertices. A vertex that is not a start or end vertex must have even degree. So far, I showed you in this picture that if I have an even degree, it's fine for me to enter and leave and enter and leave. Okay, what happens if it's odd? If I enter somewhere and then I can leave, and then I do some more of my walk and I come back and I enter and then I leave, and I do some more of my walk and I come back, there's no way for me to leave. So this right here, if you have something of odd degree, this had better be a start or an end vertex. Okay, so let's think about what we've learned. We learned that in an Eulerian walk, we can have a start, which is different from our end, and that's fine, but you can have at most one place that you start, and you can have at most one place that you end. And we learned over here that we can only have odd degree if we have a start or an end vertex. which means that we can only have an odd degree at most twice, at the start and at the end. Everywhere else, we require an even degree. So let's write that down. If a graph has an Eulerian walk, then the number of odd degree vertices is either 0 or 2. So let's think about why it's either 0 or 2. The case where we have 2 vertices of odd degree is when the start vertex is not equal to the end vertex. That's why we have 2 separate places where we start and where we end, and each of those can have odd degree. But if our start vertex is the same as our end vertex, then that one special edge that has us starting and that one special edge that has us ending coincide at our vertex to again give even degree. So this is when our start vertex equals our end vertex. We're going to have 0 vertices of degree that is odd. Okay, so now we know that if we hope to get an Eulerian walk, we're going to have either 0 or 2 vertices which have odd degree. Knowing this, let's go back up and take a look at the degrees of the graph that represents the bridges of Konigsberg. Here is the graph that represents the bridges of Konigsberg, and let's take a look at the degrees. Remember, the degree is just the number of edges that are touching a vertex. So here we have 1, 2, 3. 3. Here we also have 3. Here we also have 3. And here we have 5. Does this satisfy the property that it can have either 0 or 2 vertices of degree that is odd? No, it does not, because all of its vertices are odd. So we have 4 things that have odd degree, and by that logic, we know that it is impossible. This graph here cannot have an Eulerian walk. So not only did we solve a famous problem from the days of Euler, we have also learned the fundamental idea of what is a graph and how it can be worked with. So I'll see you next time when we give a formal definition of a graph.